All right, let's dive right into this explainer by asking ourselves a pretty fundamental question about how our brains actually work under pressure. We really love to think of ourselves as these incredibly logical creatures, perfectly weighing the pros and cons of every single choice we make. But when the stakes are high, time is running out, and other people are in the mix, what actually happens?
It's a question scientists and economists have debated for decades. Classic models treat us like rigid, perfect sculptures, calculating every single move to our maximum benefit. But the truth emerging from modern research? Well, it turns out we are spectacularly terrible at being perfect, calculating robots. In reality, we are messy, organic, and beautifully, predictably chaotic. We're driven by trust, fear, and honestly, a whole host of hidden biases.
And that brings us to the foundation we're building on today, game theory. Now, traditionally, this is the mathematical study of strategic interactions. It looks at how participants choose specific strategies to maximize their own interests based on a strict set of rules. But as we're going to see, this classic framework is currently undergoing a massive evolution to account for the simple fact that we aren't just cold calculating machines.
In this explainer, we're going to map out exactly how this evolution is playing out. We'll start with the illusion of rationality, move right into human chaos, look at trust in the ER, explore predicting the unpredictable, and finally, check out the games of the future.
Okay, part one, the illusion of rationality. Are we really as perfectly calculating as the old models assume?
We're going to trace this major paradigm shift. Historically, classical game theory assumed players were perfectly selfish robots, always seeking what's called a Nash equilibrium. It's a state where no one can improve their outcome by unilaterally changing their strategy. Think of classical theory like a hardened brick of pure logic. But predictive game theory? That's more like wet clay. It embraces bounded rationality, which is just the idea that our decisions are limited by incomplete information, our own cognitive limits, and time constraints. It actually factors in the whole messy, organic nature of human bias.
Moving right along to part two, enter human chaos. This is where we start refusing those cold equations.
Time and time again, empirical studies show that people in high-stakes situations just throw cold equations right out the window. Whether we're talking about the famous iterated prisoner's dilemma or a really complex social negotiation, humans deviate from pure selfish rationality constantly. We are driven way more by instinct, socialization, and our shared history with the people sitting across the table. And you can actually see how this chaos plays out in the data. Instead of just cutting and running to maximize their own personal payoff, which, by the way, is exactly what classic backward induction tells us to do, humans often exhibit sustained cooperation. We basically deviate from the math because our actions are molded by this evolving, probabilistic sense of trust. Bounded rationality steps in to replace perfect logic, and it ends up remolding the expected outcomes with the messy glue of human connection. All right, part three, trust in the ER. Let's look at some real high-stakes collaboration.
Let's ground this in a deeply critical, real-world scenario, a hospital emergency room. When doctors and nurses interact over time, their collaboration actually mirrors a sequential decision-making model known as centipede game theory. Basically, participants alternate between cooperating, which increases the cumulative rewards for both the patient and the staff, and defecting, which ends the interaction for an immediate personal gain, like maybe offloading a super difficult task.
But the really crucial point here is in the payoffs. The cold math strongly favors early defection. Think about it. If the physician defects and acts independently, they get a payoff of 2.08, compared to just 1.56 if they cooperate. So classical game theory dictates that the physician should defect immediately and leave the nurse hanging. But human trust completely flips the script. If you look at classical backward induction, it predicts massive early defection. At stage 1, the math says there's a 90.5% probability of someone just walking away. But researchers found something absolutely amazing. By stage 10 of the interaction, as trust builds through shared experience, human cooperation dynamically rises to 74%. Trust literally rewrites the mathematical equilibrium of the room. Which brings us to part 4. Predicting the unpredictable, where AI meets game theory.
So this leads to a massive synthesis. If humans are essentially a chaotic ball of clay heavily influenced by evolving trust and bias, how on earth do we build models that predict what they'll do at scale? Well, we turn to artificial intelligence. Researchers are now combining the strategic framework of game theory with the autonomous pattern matching of machine learning to tackle incredibly chaotic environments. A perfect example? the stock market. Here's how it works. Game theory maps out the strategic interactions and incentive structures, while machine learning adapts to new, messy human data over time. By evaluating textual data from things like social media and news articles to gauge overall investor sentiment, these algorithms can capture really subtle, nonlinear signals. So by feeding the model's data on our psychological biases and our tendency to panic, they are successfully mapping out market bubbles before they even fully materialize. Finally, Part 5, Games of the Future. Let's talk about strategic cyber warfare. This predictive, human-centric brand of game theory is now moving directly into the rapidly evolving domain of cyber warfare. Cyber defense operations are structured across these highly time-sensitive levels. You've got the strategic level for overarching goals, the operational level for planning sequences, and the tactical level for specific maneuvers, like deploying digital honeypots. And right here, AI models are attempting to predict the highly non-stationary, deeply uncertain behavior of human hackers. When modeling an attacker's behavior, analysts map out what's called the cyber kill chain. They walk through exact sequential steps: reconnaissance, planning, execution, and exploration. By anticipating this exact chain, defenders can determine exactly how and when to deploy symbiotic game models and digital deception to basically throw human attackers completely off their rhythm. You can really see the parallel games being played here. You have the attacker's kill chain, and right alongside it, the defender's response, monitoring, detection, response, and attribution. As the attacker executes their plan, the defender is simultaneously responding in this incredibly fluid, multi-agent reinforcement learning environment. The AI defender has to adapt not just to the malicious code, but to the actual psychology and bounded rationality of the human hacker on the other side of the screen. So, whether it is life-saving collaboration in an emergency room, the wild, unpredictable swings of the stock market, or a high-tech cyber battlefield, rigid, purely mathematical models will always fall short. They fail because they completely ignore the incredible, unpredictable reality of human connection, our biases, and our deep capacity for evolving trust. As these predictive game theory models become more advanced by integrating machine learning, they are getting incredibly good at mapping our wet clay. So that is the real puzzle we want to leave you with today. How might your own daily, seemingly irrational chaos be predicted by the algorithms of tomorrow? Thank you so much for joining this explainer, and keep questioning the systems trying to mold your reality.